Good morning to everyone. I feel immense pleasure to come here again for the lecture number 6, the tail contribution on static longitudinal stability related to aircraft stability and control. As you know, I am Dr. Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. So I will show this here one aircraft model. This aircraft model, this is the fuselage, this is the main wings, here is the tail, these are the vertical fins. These tails are also called the horizontal stabilizer or horizontal tail. In today's lecture, I am going to discuss how this tail will behave for making the aircraft stable, especially in longitudinal case of motion. So in this I am focusing today, and let's see, in our today's lecture we have introduction, then revision of wing contribution, because in the previous class I have discussed about contribution of the wing. Then I will discuss about tail contribution for longitudinal static stability, physics behind tail contribution. Also I will cover here next point I have not mentioned here, that is neutral point, and next point I will cover the static marching. These points I am going to cover in next 40 to 45 minutes. I will be trying to discuss these all issues. So once I talk about the introduction, we have learned from the previous classes about the longitudinal static stability. Once I talk about the longitudinal static stability, it is the ability of the aircraft to come to its equilibrium position, or in tendency of the aircraft to come to its equilibrium position whenever there is a disturbance on longitudinal motion. When I call about the longitudinal motion, the nose going up or down, this is called the pitching, and this pitching is happening in the with respect to the lateral axis. So we have to understand that in the longitudinal case, the pitching will happen, and this pitching will happen in the lateral axis, not in the longitudinal axis. But motion will be in the, this is the X and this is the Z, XZ plane. This is the XZ plane. In this plane, your aircraft will move. So we have seen in our previous class that to have the static stability, we should have two cases have to be met. First one is Cm naught should be greater than 0, or this should be positive. It is called positive. The second case, Cm alpha should be less than 0 or negative. So if I try to draw the plot of Cm versus alpha, this is the alpha, alpha means angle of attack, and this is the Cm, this side is plus, this side is minus, this side is plus, this side is minus. So if due to the disturbance some increase in angle of attack is happening, so if we draw like this a plot, this plot here, this shows that Cm naught, that is the coefficient of moment at 0 angle of attack, it should be positive. That is the Cm naught should be greater than 0, and we are able to fulfill this requirement by this plot. Second thing, what is the advantage of this CM naught positive is that we will get a trim point. This one, this is called the trim. Trim we are going to get at positive angle of attack. That is also a benefit of CM naught positive. Otherwise, your trim will be negative and you cannot fly the aircraft, because to fly the aircraft we need a positive angle of attack. Then only lift will be generated. So we have to make this configuration, and this slope of this is called CM alpha, and this should be negative. It means dCm by d alpha should be negative or less than 0. So these are the which we have already covered. I am just revisiting again in this lecture. Previously we have also referred about the contribution of the wing. So I am going to again here for the contribution of wing. So revision of the wing. We can see here, this is the red line. This red line is the wing, and here I am showing the chord of the wing. Here is the leading edge. This one is the leading edge, and this one is the trailing edge. And this line is fuselage reference line. It is called FRL, and it is a horizontal line. If you see from here, the wind direction, the free stream wind direction V is shown here, and this is making an angle alpha FRL from the horizontal, and from this chord it is called alpha wing, angle of attack of the wing, that is called alpha wing. This alpha wing, the angle of attack is measured from here, and here is wing setting angle, that is from horizontal to the chord of the wing. So here we can see that this alpha W is equal to alpha FRL minus I plus IW. So this total angle of attack is the summation of FRL, fuselage reference angle of attack, plus incidence angle or the wing setting angle of the wing. If you see this diagram, from this diagram we can see that the lift is produced perpendicular to this. It is mentioned the LW, and drag will be in the same direction in this. So this here, this will be the drag, and so the vertical here, this will be LW cos this angle, this one. Okay, so this we can write that LW minus alpha IW. Okay, so like this or FRL. Same way, the drag, horizontal drag, this is the horizontal drag here. So this will be D cos alpha W minus IW. So like this we have to divide, and we can see here that there is a CMAC of the wing also included. So now we got equation. You may be remembering in the last class number 4, we got the CG of this aircraft is equal to CLW XCG by C bar minus XACW by C bar. So you can see the XAC is measured from the here, from the leading edge, not this. This is from here to here. This is the XCG, and this is the XAC. Okay, so here XCG minus XCC. So this is the really used for the moment. So this is the XCG minus XAC. So this CMCG is equal to CLW XCG minus XCG bar minus XACW by C bar. Also CLW here is the summation of CLW is equal to CL naught plus CL alpha into alpha W. So we can see here that it is like this here. So this is the CL naught, and then here it goes CL alpha into alpha. Same way the CGW is equal to CL naught plus CL alpha into alpha. Here XCG by C bar minus XAC by C bar plus CMACW. Comparing this CMCGW is equal to CM naught W plus CM alpha into alpha, we can get that CM naught is equal to CL naught here, this term plus this. So CL naught XCG by C bar minus XAC by W and plus CMACW. And for CM alpha is equal to CL alpha W XCG by C bar minus XACW by C bar. So we got here CM naught and CM alpha. So this you can see here, what is the meaning of CM alpha? So if it is like this, this is the CM naught, and this is the CM alpha. So these two things we have to understand, then only we will be able to express this contribution of the wing. Now I want to interpretation of this previous equations. What is the interpretation of this equation and what is the message by this? If AC of the wing is behind the CG, then CM alpha is negative. So if this you can see here in this diagram, if this is the AC, this AC is behind the CG, then CM alpha here, it is a negative, minus, like this. So in this case, aircraft will be statically longitudinal stable. What will be the CM naught? As XAC is behind XCG, as XAC is behind XCG, then XCG minus XAC is negative. You can see here, this XCG is less value and this is the more value. So if we XCG minus XAC, you will get the negative value. So this CM naught will be less than 0, which we don't want, and it perhaps is cambered wing aircraft is AC is located little ahead of the CG. In this case, CM alpha is greater than 0. So if here, if you see, if the CG is behind the AC, then this will be like this. So CM naught is greater than 0, but CM alpha is also greater than 0. So we don't want CM alpha greater than 0. So how we can get the stability? Okay, so it is very critical situation. If we are putting this wing here and aerodynamic center is behind, like this, two places, this is the aerodynamic center, and if the aerodynamic center is behind the AC, it will go nose down. But same time, it will also give CM naught also negative. But we don't want CM naught negative. Okay, in the next case, if we do CG is behind the AC, then it will be nose up. It will be making nose up. So the CM alpha is positive and CM naught is also positive. So how to make this problem and how to solve this problem? So there is a issue and we are going to fix one horizontal tail, and we want to know what is the contribution of this horizontal tail. That we are going to study in this lecture. So this we can see here that here I have drawn the diagram for a wing. Here it is shown as in the previous I have shown you. This red color is a wing. From horizontal line to the relative wind V, this angle is alpha FRL, and from horizontal to the line of the chord it is wing setting angle IW, and the summation of FRL, alpha FRL plus IW is equal to alpha W. So this alpha W is equal to alpha FRL plus IW. So this is the total angle of attack here. In the previous, we have discussed how these forces L and other things, this is the D, and we want in the horizontal and in vertical direction, all these forces. So here we can see, here is the CG, this is the CG, and from this CG, the aerodynamic center is LT, and this LT is called the tail moment arm. And here we have this alpha FR is same as here, and it is also the same. And here we have a tail setting angle IT. But in this what happened, there is one more issue is coming, and that issue is here. You can see I have drawn here this diagram. In this diagram, this is the tail and this is the wing. So when the air is passing from the wing, the velocity V, which is passing from here, due to the downwash, due to the vortices are formed here, and these vortices are going downwards, and this relative wind V, which is coming in this direction V, here V, this you will not get V, but you will get V prime, and the angle between V and V prime will be epsilon, and this epsilon is called the downwash angle. This downwash angle is generated due to the formation of vortices on the wing. These vortices which are formed on the wing will move on to the horizontal tail, and horizontal tail will experience a different velocity and different angle of attack here. So it is shown here that this angle epsilon between V and this thing, and here also the same angle will be deflected, and this will be the V, and in this also this will be a drag dt, and here you have LT. So we have to take this vertical and we have to take this horizontal. So this we are going to discuss in this lecture. So here velocity vector of the tail will not be the same as wing. The wing generates the downwash, the lift and the drag are perpendicular and parallel to the effective velocity V prime. Here all the forces, this is lift and drag of the tail will be perpendicular and parallel to this V prime, not with V. And here we will see that angle of attack at the tail alpha T will be, this you can see here, that alpha W, this is alpha W minus IW is alpha FRL. So here this is the alpha FRL minus epsilon. Okay, this epsilon we have to minus and we have to add this IT. So the net angle of attack at the tail, this will be from here to here. This is the alpha FRL minus this and plus this. So this total, this to this minus this. That is the meaning of net angle of attack at the tail. It is called alpha T. Okay, so these things we have to understand that this thing will happen. Okay, so now we have to find out the tail moment arm, and this you can see here that now tail moment mt is equal to lt. This you can see minus lt, because this lift will be in this direction. So it is anti-clockwise direction, and anti-clockwise direction we have to take minus lt into lt cos alpha FRL minus epsilon. So this angle will be alpha FRL minus epsilon, this angle, plus dt vertical. So this will be sine in the same direction. So it is a plus. So plus dt means drag due to tail sine alpha FRL minus epsilon minus ZC. Okay, here is the ZC. This is the ZC from here to here. So minus ZCG dt cos alpha FRL minus epsilon means this into this. This is in the anti-clockwise into anti-clockwise direction. So it is a minus and minus LT. So this one will be the minus LT sine FRL minus epsilon, plus here you will have MAC into T. So this is added. I think it is very much clear to all how we have to take the components of this lift and the drag, and same thing is explained in our lecture number 4 for the contribution of our wing. So now we need, here we got the MT is a tail moment, but we need the coefficient of the moment. So this we want CMT, means coefficient of tail moment, CMT. This will be MT divided by half rho v square infinity SC bar. Here we have taken some approximation. Making approximation here, CLT is much greater than CD. So everywhere the CD will be 0. So this D is 0 here. Here this thing is 0 due to this approximation. ZCG is on this line here. So wherever ZCG is there, that is also ZCG, and this will also cancel. So only one term will be here, and here also we have taken cos alpha FRL minus epsilon is very small, and it is 1. So this term will be 1. So here we got that MT is equal to minus small lt into plus lt. So here we got MT is equal to minus lt into small lt. But what is the lt? Lt is a lift. So this lift is equal to half rho v square t st into clt. St is the area of the tail, and clt is a coefficient of lift for the tail. So we have to make it here that minus LT, and in place of LT we will write half rho v square T ST CLT. Wherever T is given as a subscript, it is for the tail. It indicates that it is there for tail. So now CMT is equal to MT divided by half rho v square infinity S C bar is equal to minus LT half rho v square ST into CLT divided by half rho v square infinity SC square. This indicates the wing, because the wing is experiencing a free stream velocity, and S is the area of the wing, and C bar is area of the chord of the mean chord of the wing. Now we will do a simple mathematical simplification, and we will make this half rho v square in one group, STLT into S into C bar in one group, and CLT we will make another thing. So here this minus LT ST divided by S C bar in one bracket. Another bracket we have made half rho V square T divided by half rho V square infinity into CLT. So this LT ST by SC is known as here tail volume ratio. VH is equal to ST LT by SC. So here ST means area of the tail, LT means moment arm, S is area of the wing, and C bar is chord of the wing. Here this neta is equal to half rho V square divided by half rho V square infinity. Okay, so here if just I want to express what is the meaning of tail volume ratio. This is the wing here. This wing has got the area, and this area is equal to this. If you see from the top, you will get this area. So this B into C, or this you can take the average C, and this is the span into area. So like this plus this, you will get the S. C bar is the average C of the wing. So here at the tip you have the small chord, at the root you have the big chord. You have to take average chord of the whole wing. That is called the C bar. Same way for the tail. We have the area of the tail, means this chord plus this chord by 2. It is the average chord of the tail divided by, multiplied by the span of the tail. So you will get the area of the tail, area of the wing. From here, AC of this to the CG. This is the distance from here to here is your LT. It is called the tail moment arm. That is why we put the horizontal tail far behind, so that the minimum area can be, the minimum area of the tail is needed, so that weight of the aircraft can be reduced. So this is the I have given about the VH. So the ratio of this area of tail divided by area of the wing. This is called the volume of the tail divided by volume of the wing. So this is called the tail volume ratio. Another term is here neta. Neta is equal to half rho V square tail. It is a dynamic pressure on top of the tail divided by dynamic pressure on the wing. And the value of this will be always less than 1. And also VH will be also sufficiently less. It may be 0.4, 0.3 of this. So we have got here CMT, coefficient of the tail, is equal to minus neta VH CLT. So here CLT is a coefficient of lift for the tail, VH is a tail volume ratio, and neta is equal to dynamic efficiency of the system. So we have achieved this thing, and I have explained all the parameters which are involved in this. Now I want to further clarify this thing. So now in this previous equation we got the CLT. So what is the CLT? The CLT, if you see here, this is the CLT versus alpha T. So in this, if you see, make like this. So this is the CL naught. But tail is always symmetrical. Tail is always symmetrical. So it will not be like this, but it will go like this. So here we have not added here CL naught, we have not added CL naught, not required. Okay. So that is why, otherwise if it is a cambered one, then we have to take CL naught also. So CLT is equal to CL naught plus CL alpha T into alpha T. But being we are assuming that, and mostly it is correct also, we are not only assuming, most of the aircraft, their horizontal tail are made of symmetrical airfoil. So we take CL naught as a 0. So this CLT is equal to CL alpha T in bracket alpha W minus IW, alpha W minus IW minus epsilon plus IT. So this is the alpha T. Alpha T is what? Alpha T is equal to alpha W minus IW minus epsilon plus IT. So here IT is a tail setting angle. So now the downwash can change. So this here epsilon we can write as epsilon naught plus d epsilon by d alpha into alpha W. Why we have taken here this epsilon? In the CL naught we have not taken, but we are taking here epsilon naught. It is very, very important that we have to understand. This epsilon is equal to epsilon naught plus d epsilon by d alpha into alpha wing. Oh, why we have taken this? Because this is happening due to the wing downwash created by vortices on the tail. So this will be always existing. So at 0 degree angle of attack also epsilon naught will be there, and there will be, as you change the angle of attack, d epsilon by d alpha will also change. So here we have put epsilon is equal to epsilon naught plus d epsilon by d alpha into alpha W. Now, so this d epsilon by d alpha is equal to 2CL alpha W. W indicates for wing. Wherever I am putting W, it is for the wing. So d epsilon by d alpha is equal to 2CL alpha W by pi aspect ratio of the wing, and you can also add E. But here I am assuming E is equal to 1. So I have not put E here, but if in the problem E is given, please put the value of E also. And here also epsilon is equal to 2CLW into E. So these things are required. So these things are already derived in your flight mechanics or in aerodynamics. These things are already explained in your previous semesters. So looking for the contribution of the tail, now here CLT is equal to CL alpha T. Here alpha W minus IW. For epsilon, I am writing epsilon naught minus d epsilon by d alpha into alpha W plus IT. So this minus, so this both will be minus here. Now I know that coefficient of moment of the tail is minus neta VHCLT. So minus neta VHCL alpha T here in bracket alpha W minus IW minus epsilon naught minus d epsilon by d alpha into alpha W plus IT. So further simplification, I am just taking this alpha W and this alpha W term, this term in one place. So 1 minus d epsilon by d alpha into alpha W minus IW minus epsilon naught plus IT. So now I got here that CMT is equal to minus neta VH CL alpha T 1 minus d epsilon by d alpha into alpha W minus IW minus epsilon naught plus IT. Okay, so here if you see, these terms will give the Cm naught of T and this will give Cm alpha of T. So now Cm naught T means it is a coefficient of moment. Just I am writing here this. So this is called the Cm naught T, this term, and this slope is called Cm alpha T. So this we have got here that neta VH, and here minus I have multiplied inside. So I got this plus and this minus. So epsilon naught plus IW minus IT into CL alpha T. This is the Cm naught, and Cm alpha T is equal to minus neta VH CL alpha T 1 minus d epsilon by d alpha. So this is your minus neta VH CL alpha T 1 minus d epsilon by d alpha, and this Cm naught is equal to neta VH epsilon 0 plus IW minus IT. So here we can see a very important results have come, and I am going to discuss these topics in a very detail in the next slide. So for the cambered airfoil, epsilon naught is equal to 2CL naught by pi aspect ratio. Here this you can see vertices will generate downwards at alpha is equal to 0 also. So at all the condition the downwards will be present. So epsilon naught will be there in all the condition. We cannot avoid epsilon naught. Now I want to discuss about the interpretation of the result which we have derived just now, and it is very interesting. So here I can see that how this Cm naught will be affecting the stability and the position of IW. IW means the wing setting angle. IT is a tail setting angle. These two parameters are very important, whether this Cm naught is positive or the Cm naught is negative. Okay, so I am going to discuss about this. In equation, we have find out that Cm naught T is equal to minus neta VH CL alpha T epsilon naught plus IW minus IT. Here epsilon naught is equal to 2CL naught divided by pi aspect ratio into E. So some value of epsilon naught always will be there, and why this will be there? The epsilon naught will be there as the wing will produce downwards due to vertices on the tail. It is shown here. Here I am interpreting this thing. What will be the angle of the horizontal tail? I have given here two conditions. First one, when wing is at 0 setting angle. Wind is straight line with the horizontal. The chord of this wing is in the same line as the horizontal line of this wing. If this is there, then what will be there? And second case, if your wing is in positive angle of attack. Normally, we put wing always in positive angle of attack, some 2 degree or 3 degree always we are putting. But here a very good interpretation of this equation which we have received. So we can see here that the first case, no wing setting angle. This I have made here this red color, the wing airfoil, and here we have IW is equal to 0 in this. If the IW, the wing setting angle is 0, so what will be the scenario? That you can see here. Assume that I am not considering this. I am only considering these two parameters. So if IW minus IT both are, this is 0, so this should be negative. So this result, I am not considering this. Okay, please remove this. So this, if you are putting here 0, so if you are putting here plus IT means plus 3 degree, this result it will give minus. Cm naught will be the minus, but I don't want minus. I want a plus. So IT will always be in this case negative value. And this negative, the intensity of the negative will be how much Cm naught you want positive. So this you can see here. very, very interesting, and we as the engineer, we should understand that what is the effect of this IT. So if we are putting IT, in this case, IT is equal to 1 degree. So it will be like this. Okay, this is the trim. But if I want 2 degree, it will be like this. So this CM is increasing. As you increase the IT, this CM, and if you want a 4 degree, it will be like this. So as much the requirement of this aircraft, this IT will make your aircraft in the same ratio. So it is very important parameter that the tail setting angle we have to make in such a way that Cm naught we should get positive. So this is the, now the second case I'm going to discuss about if the setting angle of the wing is positive, what will be the tail setting angle? So here if you see IW minus IT, it should be positive. So if I put here some 3 degree, so here we can, it should be less than this. So here I can put 2 degree or 1 degree or 0.5 degree. If I am putting, I am getting the value of positive. So Cm alpha will be positive. So tail setting angle should be negative for the first case, and for the second case, the difference between the wing setting angle and the tail setting angle should be positive. So we can get approximate value of Cm naught to positive. So this is the interpretation that if your wing is at 0 setting angle, you always need to make your tail as a negative, and if you have a positive wing setting, then you need to make your tail setting less than the wing setting angle. So Cm naught will be positive, and this depend upon how much Cm naught you want the positive. That much difference of these two parameters are essential. Further, I am going to discuss about neutral point, stick fixed. The neutral point is defined as that point on the longitudinal axis of the body where the aerodynamic moment does not depend upon the angle of attack, or the aircraft aerodynamic center and the neutral points are the same. The aerodynamic center and the neutral point both are directly related to the longitudinal stability of an aircraft. Both these points are distinctively different when considering stability of the aircraft. It's the center of pressure that is considered to be the same theoretically as the aerodynamic center. All the forces acting on the aerodynamic center or the center of pressure and neutral points, when coupled with the down force of the elevator or the horizontal stabilizer, defines the longitudinal stability of the aircraft. As one may know that the lift force acts through the center of the pressure, which can be coupled with the center of gravity force and will provide a nose up attitude of the aircraft. This nose up attitude is compensated by the nose down coupled form due to the elevator force and the CG deflection. Hence, for a stable flight, these couples are in balance. If the CG is placed at the neutral point, the couple force will be balanced, so that when the aircraft is disturbed in attitude, it will remain in that position until corrected. So if the CG and neutral point are in the one point, whatever deflection you will give, it will maintain in the same status. Neutral points, just I am going to derive here. So the CG location at which Cm alpha is 0 called the neutral point. If I want to find neutral point, then I have to make Cm alpha is equal to 0, or if CG moves down aircraft and both coincides, then it becomes neutral point. We now know the equation. that we have derived this, that's Cm alpha is equal to Cl alpha. This I am going to discuss in my next class, and these are the references which I have taken from the these books. So, Introduction to Aircraft Flight Mechanics, AIA Education Series by H.R. Nelson R.C. Flight Stability and Automatic Control, Tata McGraw-Hills, and NPTEL Lecture of Aircraft Stability and Control by Professor A.K. Ghosh, IIT Kanpur. Most of the things I have taken from Professor A.K. Ghosh. I thanks for his contribution, for the knowledge sharing for all the people. Thank you very much for joining, and next class we will see the neutral point in detail and its static margin and other parameters. Thank you very much for joining.
Like, share and subscribe. Hit the bell icon for more updates.